let me tell you about something that challenges our most fundamental understanding of reality observations from the James Webb Space Telescope that have led some of the world's most respected physicists to question the very nature of time itself. What JWST has found in the distant universe suggests that the arrow of time, the one-way flow from past to future that governs everything we experience, may not be as absolute as we believed. The clock is reversing. This statement sounds impossible. Time moves forward. Causes precede effects. We remember the past and anticipate the future, never the reverse. The asymmetry of time is woven into every aspect of existence, from the growth of children to the decay of stars, from the cooling of coffee to the expansion of the universe. And yet, when scientists analyze what the James Webb Space Telescope has revealed about the early universe, they find anomalies that cannot be easily explained within our standard understanding of cosmic evolution. Galaxies that should not exist, structures that form too quickly, a universe that appears, in certain respects, to be older than the time since its beginning allows. These observations have prompted some physicists to propose a radical idea that time itself may operate differently than we assume, that the arrow of time may not point exclusively forward, that in some sense, perhaps in a very deep and fundamental sense, time may be running backwards. I want to take you through what JWST has discovered and why these findings have such profound implications for our understanding of time, causation, and the nature of reality itself. Let me start with what we thought we knew about time. Time, in our everyday experience, has a clear direction. Eggs break but do not unbreak. Ice melts but does not spontaneously freeze. People age from young to old, never the reverse. This directionality, the arrow of time, seems so obvious that we rarely question it. But physics, at its most fundamental level, does not obviously require this arrow. The equations that describe the behavior of particles, Newton's laws, Maxwell's equations, Schrödinger's equation, even Einstein's equations of general relativity are time symmetric. They work equally well whether time runs forward or backward. If you filmed a simple physical process, a ball bouncing, a planet orbiting, two particles colliding, and played the film in reverse, you would see a process that is equally consistent with the laws of physics. There is nothing in the fundamental equations that forbids time reversal. And yet, the world we experience has a clear temporal direction. Why? The standard answer involves entropy, the measure of disorder in a system. The second law of thermodynamics states that entropy tends to increase over time. Ordered states become disordered. Hot objects cool. Concentrated energy disperses. This tendency creates the arrow of time we experience. But the second law raises its own question. Why does entropy increase toward the future rather than toward the past? The answer, most physicists believe, lies in initial conditions. The universe began in a state of extremely low entropy, highly ordered, highly concentrated, and has been increasing in entropy ever since. This low entropy beginning is the Big Bang, the initial state from which all cosmic evolution has followed. The arrow of time, in this view, is not fundamental to the laws of physics, but emerges from the special initial conditions of our universe. This explanation has seemed satisfying. But the James Webb Space Telescope has found something that calls it into question. Now let me describe what JWST has observed. The James Webb Space Telescope, launched in December 2021, is the most powerful astronomical observatory ever deployed. Its 6.5-meter gold-plated mirror, operating at infrared wavelengths, can detect light from the earliest galaxies in the universe, light that has been traveling for more than 13 billion years. What JWST has revealed about these early galaxies has shocked the astronomical community. The telescope has detected galaxies at redshifts exceeding 10, meaning we are seeing them as they existed less than 500 million years after the Big Bang. This alone is remarkable, pushing observation into an era previously inaccessible. But the galaxies themselves are the real surprise. They are far more massive, far more mature, and far more numerous than standard cosmological models predicted. According to the Lambda CDM model, the standard framework for understanding cosmic evolution galaxies should have formed gradually. In the early universe, dark matter should have collapsed into small halos, which then merged to form larger structures. Gas should have fallen into these halos, cooled, and formed stars. Over hundreds of millions of years, galaxies should have grown from small, irregular protogalaxies into the massive structured systems we see today. The timeline was supposed to be predictable. By 500 million years after the Big Bang, we expected to see small, young galaxies, irregular, low mass, still in the early stages of formation. What JWST found instead were massive, mature galaxies systems with stellar masses comparable to the present-day Milky Way, with disk structures, with chemical enrichment indicating multiple generations of stars, with properties that should have taken billions of years to develop. These galaxies should not exist. Or, more precisely, they should not exist at the time we observe them. They appear too old for the universe that contains them. This discrepancy has been called the impossible early galaxy problem, or more dramatically, the cosmic time crisis. It suggests that either our understanding of galaxy formation is fundamentally wrong, or our understanding of time in the early universe is incomplete. Now, let me describe the specific observations that have raised these concerns. One of the earliest JWST surprises came from a galaxy designated Glass Z13, detected in some of the telescope's first deep field observations. Preliminary analysis suggested this galaxy existed only 300 million years after the Big Bang, one of the most distant objects ever observed. But Glass Z13 was not a small primitive system. It appeared to be a substantial galaxy with a stellar mass of roughly 1 billion solar masses. Forming 1 billion solar masses of stars in 300 million years is challenging. It requires star formation rates far exceeding what typical models predict. Subsequent observations revealed more such galaxies. JADES-GSZ130, JADES-GSZ120, and others pushed the frontier of early galaxy observation while deepening the puzzle. These were not isolated anomalies. They represented a population of unexpectedly massive early galaxies. The galaxy designated GN Z11, previously detected by Hubble but studied in detail by JWST, proved particularly striking. Located at a redshift of about 10.6, corresponding to 400 million years after the Big Bang, GN Z11 is not only massive, but shows evidence of an active supermassive black hole at its center. This black hole has a mass of several million solar masses. Forming such a massive black hole in 400 million years is extremely difficult to explain. Black holes grow by accreting matter, but accretion rates are limited by radiation pressure, the outward push of light produced by the accretion process itself. Even accreting at the maximum theoretical rate, a black hole would struggle to reach several million solar masses in the time available. Yet there it is, a massive black hole in a massive galaxy existing at a time when neither should have formed. Now let me describe how these observations challenge our understanding of cosmic time. The impossible early galaxies create what might be called a temporal paradox. the galaxies appear older than the universe that contains them. This is not literally true, of course. The galaxies exist at a particular cosmic time, and their light has been traveling for a particular duration. The paradox is that the internal evolution of these galaxies, the formation of their stars, the growth of their black holes, the development of their structures seems to require more time than the age of the universe at their observed epoch. Consider an analogy. Imagine you meet someone who appears to be 50 years old, with the physical development, the experience, the maturity of a 50-year-old, but who tells you they were born only 10 years ago. You would be deeply puzzled. Either they are lying about their age, or something strange has happened to their development. The early JWST galaxies are in a similar position. They appear mature, evolved, old, but the universe they inhabit is young. Either our methods of assessing galactic age are flawed, or something has accelerated their development, or time itself has operated differently than we assume. This last possibility that time operates differently in the early universe is what has led some physicists to speak of time running backwards. Now let me explain what time running backwards could mean. The phrase time running backwards is provocative and potentially misleading. It does not mean that clocks in the early universe literally ran in reverse, or that effects preceded causes in any straightforward sense. What it means in the context of these observations is that the relationship between cosmic time and local physical processes may not be as simple as we assumed. In standard cosmology, cosmic time is defined by the expansion of the universe. 1 second of cosmic time is the same everywhere it is the time during which the universe expands by a certain factor determined by the Hubble parameter and the cosmic scale factor. Local physical processes, star formation, black hole growth, galactic evolution, are assumed to operate at rates set by local physics, unaffected by cosmic expansion. A star takes a certain amount of time to form, regardless of when in cosmic history the formation occurs. But what if this assumption is wrong? What if local processes in the early universe operated faster than they do now, so much faster that a galaxy could undergo 1 billion years of evolution in only a few 100 million years of cosmic time? This would be a sense in which time runs backwards, or more precisely, runs differently. The arrow of time would still point forward, but the relationship between cosmic time and local processes would be different in the early universe than it is today. Several physical mechanisms might produce such an effect. One possibility involves the cosmological constant, the energy density of empty space that drives the accelerating expansion of the present universe. If the cosmological constant was different in the early universe, or if dark energy had different properties, this could affect the relationship between cosmic expansion and local physics. Another possibility involves modified gravity. If gravity behaves differently at early times, stronger perhaps, or with different coupling to matter, this could accelerate structure formation, allowing galaxies to grow faster than standard models predict. Another possibility involves the nature of time itself. Some theories in quantum gravity suggest that time may be emergent rather than fundamental, that what we perceive as the flow of time arises from deeper physical processes. If time is emergent, its properties might vary under different conditions, including the extreme conditions of the early universe. Now let me describe the theoretical responses to the JWST observations. The astronomical community has responded to the impossible early galaxies with a range of theoretical proposals. The most conservative proposals involve adjustments to galaxy formation models. Perhaps star formation in the early universe was more efficient than we assumed. Perhaps the initial mass function, the distribution of stellar masses, was different, producing more massive stars that contributed more quickly to galactic mass. Perhaps feedback processes that normally limit star formation were less effective in early conditions. These proposals can explain some of the observations, but struggle with the most extreme cases. Even with optimized assumptions, it is difficult to produce galaxies with Milky Way scale masses in a few 100 million years. More radical proposals involve changes to cosmology itself. Perhaps the universe is older than we think. Perhaps there were processes before the conventional Big Bang that allowed more time for structure formation. Perhaps the expansion history of the universe was different, with periods of slower or faster expansion that affected structure formation. Some proposals invoke new physics. Perhaps dark matter has properties we have not accounted for. Perhaps it clumps more efficiently in the early universe, providing the gravitational scaffolding for rapid galaxy formation. Perhaps new particles or forces were active in the early universe that are no longer present. And some proposals, the most radical, suggest that our understanding of time itself needs revision. Dr. Claudia de Rham, a theoretical physicist at Imperial College London, has been among those suggesting that the JWST observations may point toward new physics of time. In a widely discussed paper and subsequent interviews, she has argued that the observations are impossible to ignore and may require fundamental revision of our understanding of temporal evolution in the early universe. The galaxies JWST has found are telling us something profound. De Rham has stated, either our models of galaxy formation are completely wrong, or our understanding of how time flows in the early universe is incomplete. Given how well our galaxy formation models work for the later universe, I suspect the issue is with time. This statement that the issue is with time has captured attention precisely because it challenges something so fundamental. Time is the background against which all physics occurs. If time itself varies, everything we think we understand is called into question. Now let me explore what it would mean for time to operate differently in the early universe. If time flowed differently in the early universe, if local processes occurred faster relative to cosmic expansion than they do now, several consequences would follow. First, the apparent paradox of mature early galaxies would be resolved. These galaxies would not have formed impossibly quickly. They would have formed at normal rates, but those rates would correspond to more elapsed local time than cosmic time suggests. The galaxies would be genuinely old, even though the universe that contains them is young by our reckoning. Second, the very early universe would be far more complex than we assumed. If time flowed faster there, more would have happened in the first few 100 million years than our standard picture suggests. Star formation, stellar evolution, chemical enrichment, black hole growth, all would have proceeded further than we thought possible. Third, the relationship between observations and cosmic history would need revision. When we observe a galaxy at redshift 13, we are seeing it at a particular cosmic time. But if time flowed differently then, the physical state of that galaxy does not correspond to the same amount of elapsed evolution as a similar cosmic time today. We would need to recalibrate our understanding of what observations tell us about cosmic history. Fourth, the origin of the arrow of time would need reconsideration. If time's properties varied over cosmic history, the arrow of time, the asymmetry between past and future, might not be constant. The early universe might have had a different temporal structure than the present universe. This last point is where the phrase time running backwards acquires its meaning. If the arrow of time varied, if the direction of increasing entropy, the direction of memory formation, the direction of causation were different in the early universe, this would be a sense in which time had a different character then than it does now. The arrow need not have literally reversed, but it might have been weaker or oriented differently or embedded in a different causal structure. The early universe might have been temporally strange in ways we have not conceived. Now let me examine the entropy argument more carefully. The arrow of time, as noted, is conventionally explained by entropy increase from a low entropy initial state. The Big Bang was highly ordered. Everything since has been increasing in disorder. But this explanation has always had a puzzle at its heart. Why was the Big Bang low entropy? Why did the universe begin in such a special state? This question, sometimes called the past hypothesis, has no satisfactory answer within standard physics. The low entropy initial state is simply assumed, taken as a boundary condition, unexplained by any deeper principle. Some physicists have proposed that the low entropy Big Bang is itself the consequence of deeper physics, physics that might involve time in unexpected ways. One proposal, developed by physicist Julian Barbour and others, suggests that time is emergent from a timeless underlying reality. In this view, the universe is fundamentally a static configuration of possibilities. Time and its arrow emerge from the structure of this configuration rather than being fundamental. Another proposal, developed by Sean Carroll and Jennifer Chen, suggests that the universe might be part of a larger multiverse in which entropy can increase in multiple directions from a low entropy midpoint. In some regions, entropy increases toward what we call the future. In other regions, it increases toward what we call the past. Both directions are equally valid. The distinction between past and future is local, not universal. Another proposal, developed by Roger Penrose in his conformal cyclic cosmology, suggests that the arrow of time is cyclical. The universe goes through aeons, each beginning in a Big Bang and ending in an infinitely expanded future. The endpoint of one aeon becomes a starting point of the next through a conformal transformation that resets entropy. Each of these proposals involves time operating differently than our everyday experience suggests. And each might have implications for the early universe that could connect to the JWST observations. Now let me describe what time running backwards might mean in the context of these theories. In Barbour's timeless picture, the early universe would not be early in any fundamental sense. All configurations, early and late, simple and complex, would coexist timelessly with the appearance of temporal evolution emerging from their relationships. The impossible early galaxies might be configurations that exist in the timeless structure but appear, from our time-bound perspective, to be temporally anomalous. In Carroll and Chen's picture, the early universe might be close to the entropy minimum, the midpoint from which entropy increases in both temporal directions. Near this minimum, the arrow of time might be weak or even ambiguous. Processes that appear time asymmetric in the late universe might be more symmetric near the Big Bang. Galaxies might form in ways that do not follow the usual temporal logic. In Penrose's picture, the early universe of our aeon might contain imprints from the previous aeon signals that have, in a sense, traveled backward through the conformal boundary between eons. These imprints might affect structure formation, providing seeds for galaxies that allow them to form more quickly than expected from our aeon's initial conditions alone. Each of these scenarios involves time operating differently than we normally assume. Each could, in principle, help explain the impossible early galaxies. And each would have profound implications for our understanding of time, causation, and reality. Now let me consider what observations might distinguish these possibilities. The JWST observations that have sparked this discussion are statistical. They concern the population of early galaxies, their masses, their abundances, their properties. These observations constrain theoretical possibilities, but do not uniquely determine explanations. To distinguish between different theoretical proposals, we would need more specific predictions and more targeted observations. If the issue is galaxy formation physics rather than fundamental time, we would expect the anomalies to be quantitative rather than qualitative. Early galaxies might be more massive than expected, but they should still follow the basic patterns of galactic evolution. Their stellar populations should still age in normal ways. Their chemical abundances should still reflect normal nucleosynthesis. Their structures should still follow normal dynamical laws. If the issue is cosmological, different expansion history, different dark energy properties, we would expect signatures in other observables. The cosmic microwave background might show anomalies. The distribution of galaxy clusters might differ from predictions. The relationship between redshift and distance might be slightly altered. If the issue is fundamental time, the signatures might be more subtle and more strange. We might see correlations that violate normal causation effects that precede their causes, or structures that have no apparent causal origin. We might see asymmetries that reverse at different cosmic epochs. We might see phenomena that are not time reversal invariant in ways that current physics does not explain. These signatures would be extraordinary and extraordinarily difficult to detect, but the stakes are correspondingly high. If time itself operates differently in the early universe, this would be one of the most profound discoveries in the history of science. In part 2, I want to explore the theoretical frameworks in greater depth to understand what physics might underlie differential time flow and what the implications would be for our understanding of causation, entropy, and the nature of reality itself. So we've established what the James Webb Space Telescope has observed galaxies in the early universe that appear too massive, too mature, too evolved for the time available since the Big Bang. We've seen how these observations have led some physicists to question the nature of time itself, proposing that time may have operated differently in the early universe. Now, I want to explore the theoretical frameworks that might explain such differential time flow. What does physics actually say about the nature of time? How could time behave differently under different conditions? And what would it mean for our understanding of causation and reality if these proposals are correct? Let me begin with the deepest question. What is time? This question, seemingly simple, has occupied philosophers and physicists for millennia. We all experience time, the flow from past to future, the accumulation of memories, the anticipation of events to come. Time seems as fundamental as space, as basic as existence itself. But when we try to define time precisely, difficulties emerge. Is time something that exists independently of events, a stage on which the universe performs? Or is time merely the sequence of events themselves with no existence apart from them? Is time continuous, flowing smoothly like a river? Or is it discrete, composed of minimal units that cannot be further divided? Is time universal, the same everywhere for everyone? Or is it relative, varying depending on motion and gravity? Is time fundamental, a basic ingredient of reality? Or is it emergent, arising from deeper structures that are themselves timeless? Physics has provided partial answers to some of these questions. Einstein's relativity showed that time is relative. It passes at different rates for observers in different states of motion or in different gravitational fields. Two observers who start synchronized can end up with different elapsed times depending on their histories. This relativity of time is experimentally confirmed. Atomic clocks flown on aircraft run slightly slower than identical clocks on the ground. GPS satellites must account for relativistic time differences to function accurately. Time dilation is not philosophy, it is engineering. But relativity does not explain the arrow of time. Einstein's equations are time symmetric. They do not distinguish past from future. The directionality of time, the fact that we remember yesterday but not tomorrow, that eggs break but do not unbreak, comes from elsewhere. The standard explanation, as we discussed, involves thermodynamics. Entropy increases toward the future because the universe began in a low entropy state. The arrow of time is not fundamental to the laws, but arises from the initial conditions. But this explanation is incomplete. It does not explain why the initial conditions were low entropy. It does not explain why entropy increase defines the arrow of time rather than some other asymmetry. It assumes what it seeks to explain. The JWST observations have reopened these questions. If the early universe contained structures that should have taken longer to form, perhaps the relationship between entropy, time, and causation was different then. Perhaps the arrow of time was different. Perhaps time itself was different. Now let me explore what different time might mean physically. In general relativity, time is not separate from space. The two are woven together into a four-dimensional fabric called space-time. Events are located not just in space, but in space-time. They have coordinates that specify where and when they occur. The geometry of space-time is determined by the distribution of matter and energy. Mass curves space-time, and this curvature is what we experience as gravity. Near massive objects, space-time is more curved. Clocks run slower. Objects follow curved paths. The geometry differs from the flat space-time of empty space. In the early universe, conditions were extreme. Densities were enormous, temperatures were vast, the curvature of space-time was intense. Under these conditions, the properties of space-time, including potentially the properties of time, might have been different from what we experience today. One possibility involves the rate at which time passes relative to physical processes. In relativity, there is no absolute rate of time. Time passes at different rates in different reference frames, and all rates are equally valid. But there is a local proper time, the time experienced by a clock moving with a particular observer that provides a standard for measuring local processes. What if, in the early universe, the relationship between proper time and physical processes was different? What if clocks ran at the same rate, but physical processes, star formation, black hole growth, chemical evolution, proceeded faster relative to those clocks? This would not violate relativity. It would involve a change in the coupling between time and other physical fields. The clock would still measure time correctly, but the processes it was timing would occur more rapidly. Such a change might arise if fundamental constants varied over cosmic history. The speed of light, the gravitational constant, the strength of nuclear forces, if these were different in the early universe, physical processes would proceed at different rates. A star might form faster if nuclear reactions were stronger. A black hole might grow faster if gravity was more intense. Theories with varying constants have been proposed and constrained by observations. Most measurements suggest the constants have been stable over cosmic history, but the constraints are imperfect. And small variations, particularly in the extreme conditions of the very early universe, cannot be ruled out. Another possibility involves the dimensionality of time itself. We normally assume that time has one dimension, a single line from past to future. But some theoretical frameworks propose multiple time dimensions. In string theory, the mathematics sometimes suggests additional temporal dimensions beyond the familiar one. If the early universe had access to additional time dimensions that are now compactified or inaccessible, processes might have evolved in ways that do not map simply onto our single-dimensional time. A galaxy might have aged along one time dimension while appearing young in another. This possibility is highly speculative. We have no direct evidence for additional time dimensions, and the theoretical frameworks that suggest them are not observationally confirmed. But the JWST observations create pressure to consider possibilities that would otherwise seem implausible. Now let me examine the thermodynamic arrow of time more carefully. The arrow of time defined by entropy increase is called the thermodynamic arrow. It is the arrow that governs heat flow, chemical reactions, the mixing of substances, the approach to equilibrium. But there are other arrows of time that might or might not align with the thermodynamic arrow. The cosmological arrow points in the direction of cosmic expansion. The universe is expanding now. The future is larger than the past. This arrow could, in principle, reverse if the universe began contracting. The radiative arrow concerns the direction in which electromagnetic waves propagate. We observe retarded waves, waves that spread outward from sources, rather than advanced waves that converge on absorbers. The radiative arrow appears to align with the thermodynamic arrow, but the relationship is not fully understood. The quantum arrow involves the direction of wave function collapse. In quantum mechanics, measurements cause superpositions to collapse into definite states. This collapse appears to be irreversible. The arrow points from superposition to definiteness, but whether this arrow is fundamental or emergent is debated. The psychological arrow is the direction of memory and experience. We remember the past and anticipate the future, never the reverse. This arrow appears to be connected to the thermodynamic arrow memory formation, is an entropy increasing process, but the connection is not fully explained. In our current universe, these arrows all align. The thermodynamic arrow points from past to future, so do the cosmological, radiative, quantum, and psychological arrows. Everything is consistent. But what if, in the early universe, the arrows did not align? What if some processes pointed one direction while others pointed differently? This misalignment might create conditions that appear paradoxical from our perspective. Structures might form that seem to violate causation as we understand it. Events might occur in sequences that do not match our expectations of before and after. The impossible early galaxies might be evidence of such misalignment. If the thermodynamic arrow in the early universe was oriented differently, or if it was weaker, allowing entropy to fluctuate in both directions, structures might have formed in ways that appear impossible when viewed through the lens of our current temporal structure. Now let me explore what quantum mechanics says about time. Quantum mechanics has a peculiar relationship with time. In most formulations, time is a parameter, a label attached to quantum states rather than an observable that can be measured like position or momentum. This asymmetry between space and time in quantum mechanics is one of the deepest puzzles in physics. General relativity treats space and time symmetrically. Quantum mechanics treats them differently. Reconciling these treatments is one of the major challenges in developing a theory of quantum gravity. Some approaches to quantum gravity suggest that time might be emergent, that it arises from more fundamental structures that are themselves timeless. In the Wheeler-DeWitt equation, a foundational equation and one approach to quantum gravity, time does not appear at all. The equation describes the quantum state of the universe without reference to time. Time, in this view, must emerge from the relationships between different parts of the quantum state, rather than being fundamental. This timeless picture might seem abstract, but it has implications for the early universe. If time emerges from quantum gravitational effects, and if those effects were stronger in the extreme conditions of the early universe, time might have been less sharply defined then. The distinction between past and future might have been blurry rather than crisp. In such conditions, structures might form in ways that do not follow normal causal logic. Galaxies might emerge from quantum states in which their formation process is not well defined, in which they simply exist without a clear history of assembly. This sounds paradoxical, but quantum mechanics is full of paradoxes. Particles can be in superpositions of different states. They can be entangled across vast distances. They can interfere with themselves as if traveling multiple paths simultaneously. A universe in which time is emergent might exhibit temporal paradoxes analogous to these spatial and quantum ones. Now let me consider the role of entropy in more detail. Entropy, as normally defined, measures the number of microscopic configurations consistent with the macroscopic state of a system. A high entropy state is one that can be realized in many ways. A low entropy state can be realized in few ways. The second law of thermodynamics states that entropy tends to increase because high entropy states are more probable than low entropy states. If a system starts in a low entropy state, random fluctuations will almost certainly carry it toward higher entropy. The increase is not certain. Entropy can decrease by fluctuation, but overwhelmingly probable. This statistical explanation of the second law is well established. But it raises the question of why the universe began in a low entropy state. The early universe was hot and dense conditions that might seem disordered. But from a gravitational perspective, the early universe was highly ordered. Gravity tends to clump matter together. A uniformly distributed gas is gravitationally low entropy. The smooth, uniform early universe was a gravitational improbability from which entropy has been increasing ever since. If the early universe had different gravitational properties, if gravity was stronger or differently coupled to matter, the entropy accounting might be different. What appears low entropy to us might have been high entropy by the standards that applied then. This possibility connects to the JWST observations. If gravitational entropy was defined differently in the early universe, the arrow of time might have pointed differently. Processes that increase entropy today might have decreased it then, or might have been entropically neutral, allowed to proceed in either temporal direction. In such conditions, galaxies might form more quickly than our entropy calculations suggest. The constraints that limit structure formation, constraints rooted in entropy increase, might have been weaker or absent. Now let me examine specific theories that propose modified time in the early universe. Several theoretical frameworks propose that time behaved differently in the early universe. Let me describe some of the most developed loop quantum cosmology. An approach to quantum gravity based on loop quantum gravity suggests that the Big Bang was not the beginning of time, but a transition, a bounce from a previous contracting phase. In this picture, time extends infinitely into the past and future, with the Big Bang representing a moment of maximum curvature rather than a boundary. Near the bounce, the properties of space-time differ dramatically from our current experience. Quantum gravitational effects dominate. The classical notions of space and time break down. In this regime, the arrow of time might be ill-defined or might point in the opposite direction on either side of the bounce. If echoes of the pre-bounce phase persist into our aeon, if information somehow crosses the bounce, this might affect structure formation in the early post-bounce universe. Galaxies might form more quickly because they have, in some sense, precursors from before the bounce. Conformal cyclic cosmology, proposed by Roger Penrose, suggests that the universe goes through infinite cycles called eons. Each eon begins with a Big Bang and ends in an infinitely expanded future dominated by radiation. The endpoint of one aeon becomes, through conformal rescaling, the starting point of the next. In CCC, information can cross between aeons. Gravitational waves from collisions between supermassive black holes in the previous aeon might appear as circular patterns in our CMB. More speculatively, other information might cross patterns that affect how structure forms in the new aeon. If such cross-aeon information affects galaxy formation, The apparent age of early galaxies might reflect processing that occurred in the previous aeon. The galaxies would not have formed quickly in our time. They would carry information from a previous time that accelerated their formation. The cosmological natural selection hypothesis, proposed by Lee Smolin, suggests that black holes give birth to new universes with slightly different physical parameters. Universes that produce many black holes are more fit and become more common in the multiverse. In this framework, our universe might have parameters, including parameters affecting the rate of structure formation that differ from a naively expected baseline. Time might flow differently, or processes might proceed faster, because our universe descended from ancestors with similar properties. Each of these frameworks proposes that the simple picture of time, a uniform flow from Big Bang to present, is incomplete. Each suggests that the early universe had temporal properties that differ from our current experience, and each might help explain the JWST observations. Now let me consider what observations might test these ideas. The theoretical frameworks I've described make different predictions that might, in principle, be observationally distinguished. Loop quantum cosmology predicts specific modifications to the CMB power spectrum at the largest scales. The bounce would leave imprints deviations from the standard inflationary predictions that should be detectable with sufficiently precise measurements. Current observations do show some anomalies at large scales, but whether they match LQC predictions is debated. Conformal cyclic cosmology predicts circular patterns in the CMB from gravitational waves crossing between aeons. Penrose and collaborators have claimed to detect such patterns. Critics have argued that the claimed patterns are consistent with random noise. The debate continues. With no clear resolution, varying constants would leave signatures in the spectra of distant objects. If the fine structure constant or the proton to electron mass ratio were different in the early universe, atomic transitions would occur at slightly different energies, shifting spectral lines in detectable ways. Current observations constrain such variations, but cannot rule out small changes at very high redshift. More generally, if time operated differently in the early universe, we might expect to see correlations that violate standard causation. Effects might appear to precede causes. Structures might exist without apparent formation mechanisms. Patterns might recur in ways that have no causal explanation. Such acausal correlations would be extraordinary evidence. They would be difficult to establish because our entire framework for interpreting observations assumes causation. We might see causal patterns and interpret them causally, missing their true significance. The JWST observations might already contain such patterns. The impossible early galaxies are unexplained within standard causation. They appear to be effects without adequate causes, structures that exist without the time needed to create them. If we take this at face value, we might already be seeing evidence of modified time. The galaxies are not impossible. They are merely impossible within our causal framework. If the framework is wrong, if causation in the early universe differed from causation, now the galaxies become possible. Now let me consider the philosophical implications. If time operated differently in the early universe, if the arrow of time was weaker or differently oriented or emergent rather than fundamental, this would have profound philosophical implications. First, it would challenge our intuitions about causation. We assume that causes precede effects, that the past determines the future, that explanations flow backward in time. If time's arrow was different in the early universe, these assumptions might fail. Events might occur without causes, or with causes that post-date them by our reckoning. This does not mean anything goes. Even in frameworks with modified time, There are constraints, physical laws, conservation principles, consistency requirements. But the constraints might be different from those we intuitively expect. Second, it would challenge our understanding of history. We assume that the universe has a single history, a sequence of events from Big Bang to now. If time was different in the early universe, the notion of a single history might be inadequate. The early universe might have multiple histories, or an indefinite history, or a history that cannot be mapped onto our temporal framework. This has implications for cosmology as a historical science. We try to reconstruct the history of the universe from current observations. If the early universe had different temporal properties, this reconstruction might be fundamentally limited. We might not be able to specify what happened before a certain point because before might not have its usual meaning. Third, it would challenge our understanding of ourselves. Human experience is deeply temporal. We remember the past. We anticipate the future. We experience the present as a fleeting moment between them. If time is not fundamental, if it emerges from deeper structures, if its properties vary, then our temporal experience is not a direct perception of reality, but a constructed interpretation. This is not necessarily troubling. We already know that much of our experience is constructed. Colors are not properties of objects, but interpretations of wavelengths. Sounds are not properties of events, but interpretations of pressure waves. If time is similarly constructed, this would extend a pattern we already recognize. But it would be strange. Time feels more fundamental than color or sound. The flow from past to future, the irreversibility of events, the accumulation of memory, these seem to be features of reality itself, not merely of our perception. If they are features of perception, if time as we experience it is an emergent, contingent, variable phenomenon, then reality itself is stranger than we imagined. In part 3, I want to explore the deepest implications of these ideas, what they mean for our understanding of existence, for the possibility of other forms of temporal experience, and for the future of cosmology as we continue to probe the early universe. So we've established what the James Webb Space Telescope has observed and explored the theoretical frameworks that might explain those observations: loop, quantum cosmology, conformal cyclic cosmology, emergent time, varying constants, modified arrows of time. We've seen how these frameworks challenge our understanding of causation and history. Now I want to explore the deepest implications. What would it mean for our understanding of existence if time is not what we thought? What might we discover as we continue to probe the early universe? And what does this tell us about the nature of reality itself? Let me begin by considering what it means for time to be emergent. The idea that time might emerge from deeper structures rather than being fundamental has gained traction in theoretical physics over the past few decades. Several approaches to quantum gravity suggest that space-time itself is not basic but arises from more primitive ingredients. In loop quantum gravity, space-time is woven from discrete units called spin networks. These networks have no inherent notion of space or time. Space and time emerge from the relationships between network elements. At the Planck scale, the smallest meaningful scale in physics, space-time dissolves into a quantum foam of fluctuating geometry. In string theory, space-time emerges from the dynamics of strings and branes in higher dimensional spaces. The familiar 4 dimensions of space-time are not fundamental, but arise from particular configurations of the theory. Other configurations might give rise to different numbers of dimensions, different geometries, different temporal structures. In approaches based on quantum information, space-time emerges from patterns of entanglement between quantum systems. The geometry of space reflects the entanglement structure of the underlying quantum state. Time emerges from the evolution of this entanglement from the flow of quantum information through the network. Each of these approaches suggests that time, as we experience it, is not a basic feature of reality. It is a derived feature emerging from structures that are themselves timeless or differently temporal. If time is emergent, its properties might vary. In different regions of the universe, under different conditions, time might emerge with different characteristics. The arrow of time might point differently, the rate of time might vary, the very dimensionality of time might differ. The early universe, with its extreme conditions, might be a region where time emerged with different properties than it has today. The impossible early galaxies might be evidence of this, structures that formed under a different temporal regime, appearing anomalous when viewed through our current temporal framework. Now let me explore what different temporal properties might mean concretely. Consider the rate of time. In our experience, 1 second is 1 second everywhere, the same duration, the same capacity for events to occur. But if time is emergent, its rate might depend on conditions. Near the Big Bang, where quantum gravitational effects were strong, time might have flowed faster or slower relative to physical processes. If time flowed faster, if more time elapsed per unit of physical process, then structures could evolve further in a given amount of cosmic time. A galaxy that appears to have undergone 1 billion years of evolution might have genuinely experienced 1 billion years of local time, even though cosmic time suggests only a few 100 million years have passed. This is not mere time dilation, as in relativity. Relativistic time dilation affects both clocks and physical processes equally. A clock in a gravitational field runs slow, but so do all processes. So the clock still accurately measures local time. What I'm describing is a decoupling time flowing at one rate while processes proceed at another. Such a decoupling would violate standard physics, but standard physics might not apply in the extreme conditions of the early universe. Quantum gravity might introduce corrections that allow rate mismatches we do not experience under ordinary conditions. Consider the dimensionality of time. We experience time as one-dimensional, a single line from past to future. But mathematics allows for multiple time dimensions. In a universe with 2 time dimensions, a particle could evolve along either dimension independently, accessing a plane of temporal possibilities rather than a line. Additional time dimensions are usually considered problematic. They tend to introduce instabilities and paradoxes, effects preceding causes, closed time-like curves, violations of energy conservation. Physicists typically assume that viable physical theories have exactly 1 time dimension. But in the very early universe, when quantum gravity dominated, additional time dimensions might have been accessible. They might have since compactified, curled up too small to affect physics, or become inaccessible as the universe expanded and cooled. Remnants of their influence might persist in the structure of the early universe. A galaxy that evolved in a 2-dimensional time might have explored temporal possibilities unavailable to us. It might have assembled more efficiently by accessing pathways through the time plane that do not exist in our 1-dimensional time. When we observe it, we see only the projection onto our single time dimension, a projection that appears impossibly rapid. Consider the arrow of time. We experience time as irreversible. Eggs break, entropy increases, the past is fixed while the future is open. But if time is emergent, its arrow might be a property of the emergence rather than a fundamental feature. In the very early universe, when time was just emerging, the arrow might have been undefined or fluctuating. Entropy might have been able to increase or decrease with equal probability. Processes might have been reversible in ways they are not today. Under such conditions, structure formation might proceed differently. The constraints that limit assembly thermodynamic irreversibility, the cost of entropy reduction, might have been weaker. Galaxies might have formed through processes that are thermodynamically forbidden in the current universe. When we observe these galaxies, we interpret them through our arrow of time. We assume that their evolution proceeded from simple to complex, from past to future, constrained by entropy, increase. But if their formation occurred when the arrow was undefined, this interpretation might be wrong. They might have assembled through processes that have no analog in our temporal experience. Now let me consider the implications for causation. Causation, the relationship between cause and effect, is intimately connected to the arrow of time. Causes precede effects. This is part of what we mean by cause and effect. The arrow of time defines which direction causal influence flows. If the arrow of time was different in the early universe, causation might have operated differently too. One possibility is retrocausation, causal influence flowing backward in time. In our experience, the past causes the future, never the reverse. But if the arrow was undefined or bidirectional in the early universe, future states might have influenced past states. Effects might have preceded causes. This sounds paradoxical, but retrocausation is not entirely foreign to physics. In quantum mechanics, some interpretations involve retrocausal effects. The two-state vector formalism, for example, describes quantum systems using both past and future boundary conditions with causal influence flowing in both temporal directions. If retrocausation operated in the early universe, the impossible early galaxies might have been caused partly by their future states. Their formation might have been guided by conditions that had not yet occurred, conditions that, from our perspective, lie in their future. This would explain the appearance of excessive maturity. The galaxies would not have evolved rapidly through normal forward causal processes. They would have been shaped by both past and future, assembled through temporal pathways that include both directions of time. Another possibility is a causal structure. In our experience, every structure has causes. It results from prior conditions through lawful processes. But if time was emergent and incomplete in the early universe, some structures might exist without causes. They might simply be features of the initial state that have no explanation in terms of prior events. This possibility is disturbing to our causal intuitions. We want to ask, how did this form? And expect an answer involving earlier conditions and formation processes. But if the question is malformed, if there was no earlier in the relevant sense, the structure might have no causal explanation. The impossible early galaxies might be such structures. They might not have formed at all in the usual sense. They might have existed from the earliest definable moment, features of the primordial state rather than products of evolution. This interpretation makes the galaxies genuinely mysterious. They would not be the result of rapid formation, but of no formation existence without origin, structure without history. Now let me consider what this means for our understanding of the Big Bang. The Big Bang, in standard cosmology, is the beginning of time. There is no before the Big Bang. Time itself begins with the initial singularity. Questions about what caused the Big Bang are meaningless because causation requires time, and time did not exist before there was time. This picture has always been uncomfortable. Our intuition rebels against beginnings without causes. We want to ask what caused the Big Bang, even if the question is ill-formed. The proposals I've been discussing offer alternatives. In loop quantum cosmology, the Big Bang is not a beginning, but a bounce, a transition from a previous contracting phase. Time extends infinitely into the past. There is no beginning. The impossible early structures might carry information from before the bounce, explaining their apparent maturity. In conformal cyclic cosmology, the Big Bang is a transition between aeons. The previous aeon's infinite future becomes our Big Bang through conformal rescaling. Time is cyclical. There is no ultimate beginning, only transitions between cycles. Structures in our aeon might reflect processing in previous aeons. In eternal inflation, the Big Bang is a local event in an infinite multiverse. Inflation has been occurring forever, spawning bubble universes without end. Our Big Bang is the formation of our bubble. There is no beginning to the multiverse as a whole. Our bubble's early structures might be influenced by multiverse-level processes. Each of these proposals extends time beyond the conventional Big Bang, eliminating the need for a beginning and potentially explaining the impossible early galaxies, but each also raises new questions. If the Big Bang is a bounce, what happened in the contracting phase? If it is a transition between aeons, what began the first aeon? If it is a local event in an eternal multiverse, what sustains the multiverse's existence? These questions push the mystery backward without eliminating it. There may be no final answer, no ultimate explanation that does not raise further questions. The chain of causes might extend infinitely, or it might bottom out in something that simply is without cause or explanation. Now let me consider the implications for consciousness and experience. Our experience of time, the flow from past to future, the accumulation of memory, the anticipation of what is to come is central to what it means to be conscious. We experience ourselves as persisting through time, as having histories that shape who we are, as facing futures that we can influence through our choices. If time is emergent rather than fundamental, what does this mean for our experience? One possibility is that our temporal experience is a feature of the emergence, a property that arises when consciousness interacts with the emergent temporal structure. Just as color emerges from wavelength, just as temperature emerges from molecular motion, the experience of temporal flow might emerge from the interaction between consciousness and the underlying timeless reality. This possibility has been explored by philosophers and physicists working at the intersection of consciousness and quantum gravity. Some have proposed that consciousness plays a role in the emergence of time, that the observer and the observed co-constitute temporal reality. Such proposals are speculative and controversial, but they suggest that temporal experience might not be universal. Different forms of consciousness, or consciousness under different conditions, might experience time differently or might not experience time at all. In the early universe, before time had fully emerged, conscious observation, if any existed, might have been atemporal. There might have been awareness without sequence, existence without duration, being without becoming. This is difficult to imagine because our imagination is temporal. We think in sequences, in before and after, in narratives that unfold over time. An atemporal existence is almost inconceivable from our perspective. But our perspective is limited by our cognitive architecture, which evolved in a temporal environment. The universe is not obligated to conform to our cognitive limitations. Temporal experience might be local rather than universal, a feature of consciousness in our region of reality rather than a fundamental property of consciousness itself. Now let me consider what future observations might reveal. The James Webb Space Telescope has opened a window onto the early universe that previous instruments could not access. But JWST is just the beginning. Future observatories will probe even earlier epochs with greater sensitivity and resolution. The Nancy Grace Roman Space Telescope, planned for the late 2020s, will survey vast areas of sky, detecting millions of distant galaxies. Its wide field of view will complement JWST's deep, narrow observations, providing statistical power to characterize the population of early galaxies. Next-generation ground-based telescopes, the extremely large telescope, The 30-meter telescope, the Giant Magellan Telescope, will provide unprecedented resolution and sensitivity. They will be able to study individual early galaxies in detail, measuring their kinematics, their chemical abundances, their stellar populations, gravitational wave observatories, LIGO, Virgo, CAGRA, and eventually the space-based LISA will detect gravitational waves from the early universe. Primordial gravitational waves, if they exist, carry information about conditions during and shortly after the Big Bang. They might reveal signatures of modified time or alternative cosmologies. Cosmic microwave background experiments, CMB, S4, and others will measure the polarization of the CMB with exquisite precision. This polarization carries information about inflation and the very early universe. Anomalies in the polarization might indicate modified time or non-standard initial conditions. These observations will provide data to test the theoretical frameworks I've described. They will either confirm standard cosmology requiring explanation of the early galaxies within conventional physics, or reveal further anomalies that strengthen the case for modified time. Either outcome will advance our understanding. Science progresses through the interplay of observation and theory, each informing and constraining the other. The JWST observations have created pressure for new theory. Future observations will test whatever theories emerge. Now let me consider the possibility that time modification is an illusion. I have presented the case for modified time in the early universe, but I should acknowledge that this case is not proven. The JWST observations are surprising, but surprising observations have often been explained within conventional frameworks. Perhaps the early galaxies are not as massive as they appear. Mass estimates from photometry are uncertain. Spectroscopic measurements might reveal that the masses have been overestimated. Perhaps the stellar populations are unusual, producing more light per unit mass than conventional populations. Perhaps the black holes are not as massive as they appear. Black hole mass estimates from line widths are model dependent. Different models might yield different masses. Perhaps the black holes form through exotic mechanisms, direct collapse of gas clouds, primordial black holes that circumvent the usual growth limits. Perhaps the cosmological model is slightly wrong. Perhaps the expansion history differs from lambda CDM in ways that affect distance and age estimates. Perhaps there was an early period of non-standard expansion that allowed more time for structure formation. Perhaps galaxy formation theory is incomplete. Perhaps feedback processes, merger rates, or star formation efficiencies differ from current models in ways that allow faster growth. Perhaps theoretical uncertainties have been underestimated. Each of these possibilities offers a conservative explanation for the observations, an explanation that does not require revising our understanding of time. Scientists should pursue these possibilities energetically before concluding that something as fundamental as time needs revision, but I will note that the observations have persisted and multiplied. Each new JWST dataset has revealed more early galaxies, more massive structures, more apparent impossibilities. The surprises have not diminished as data have accumulated. They have grown. If the conventional explanations are correct, we should expect the anomalies to resolve as we understand the systematic effects better. If the anomalies persist, if every adjustment to the conventional framework is met with new surprises, this will strengthen the case for something more radical. Now let me reflect on what it would mean for time to be running backwards. The phrase, time is running backwards, is dramatic and potentially misleading. Time in the early universe probably did not literally run in reverse, with effects preceding causes, with entropy decreasing, with the arrow pointing from future to past. But the phrase captures something important. It captures the sense that our intuitive understanding of time may not apply everywhere and always. It captures the possibility that time has properties, direction, rate, dimensionality that can vary. It captures the recognition that time, like space, might be subject to the laws of physics rather than being the background against which physics occurs. If time can vary, then our temporal experience is not a universal truth. It is a local feature, characteristic of our region of space-time, arising from conditions that might be different elsewhere or elsewhen. This is both humbling and exhilarating. It is humbling because it reveals the limitations of our perspective. We are temporal creatures embedded in a particular temporal structure, unable to directly perceive or imagine alternatives. Our temporal intuitions, however compelling, might be parochial rather than universal. It is exhilarating because it opens possibilities. If time can vary, if temporal experience is not fixed, then reality is richer than we imagined. There might be modes of existence we cannot conceive, atemporal, multitemporal, reversibly temporal, that are as real as our own but inaccessible to our experience. The early universe, in this view, was not simply earlier than now. It was different, differently temporal, differently causal, differently structured. The impossible early galaxies are impossible only from our temporal perspective. From the perspective of their own temporal regime, they might be perfectly normal, or the very concept of normal might not apply. Now let me consider the connection between time and existence. Time is intimately connected to what it means to exist. We exist in time. Our existence has duration. We persist from moment to moment, changing yet remaining the same. If time is not fundamental, if it emerges from timeless structures, then existence itself might be atemporal. The fundamental reality might not exist in time because time is not fundamental. Reality might simply be without duration, without change, without becoming. This is difficult to reconcile with our experience. We experience change constantly. We see the world transform, we feel ourselves age, we remember the past and anticipate the future. How can this temporal experience arise from an atemporal reality? One answer is that temporal experience is perspectival. From within the atemporal whole, we experience a sequence because of how we are embedded in that whole. Different parts of the timeless structure are experienced as different times. The appearance of change is a feature of our perspective, not of reality itself. This is sometimes called the block universe view. In this view, all of time, past, present, and future, exists equally. There is no objective now, no flow of time, no becoming. The present moment is not special. It is simply where we find ourselves in the block. The block universe view is controversial. Many philosophers and physicists find it difficult to reconcile with our vivid experience of temporal flow. But it is consistent with the physics of relativity, which does not privilege any moment as now and treats time as a dimension similar to space. If the block universe view is correct, the early universe exists. Not existed in the past tense, but exists timelessly in the same sense that distant galaxies exist spatially. The impossible early galaxies exist in the block. They are features of the atemporal whole, not products of temporal evolution. This perspective does not explain the galaxy's structure. It does not tell us why that particular pattern exists in the block, but it dissolves the temporal paradox. The galaxies do not need time to form, because formation is a temporal concept and time is not fundamental. They simply are part of reality's atemporal structure. Now let me consider what this means for the future. If time's properties can vary, what about the future of our universe? Might time change again? As the universe continues to expand and evolve, several possibilities present themselves. As the universe expands and cools, quantum gravitational effects become ever more negligible. The conditions that might have supported modified time in the early universe are increasingly absent. Time, in this view, should become more stable, more uniform, more like our everyday experience as cosmic history proceeds. But the far future might bring new conditions. If dark energy increases, if the universe approaches a big rip space-time might again enter an extreme regime, quantum gravitational effects might become relevant, time's properties might again become strange, or if the universe eventually collapses, if dark energy reverses and gravity wins, the Big Crunch might recreate conditions similar to the Big Bang. Time might again become emergent. The arrow might again become ambiguous. Causation might again become strange. Or if the universe is cyclic, bouncing, or transitioning between aeons, we might be partway through a cycle in which time's properties vary. The early stages had different time, so might the late stages. Our current experience might be a temporary condition between extremes. These possibilities are speculative, but they are consistent with the theoretical frameworks that take time to be emergent rather than fundamental. If time can vary, its future is as uncertain as its past. Now let me conclude with a reflection on what the JWST observations mean. The James Webb Space Telescope has shown us a universe that does not match our expectations. Galaxies that should not exist, structures that formed too quickly, a cosmic history that does not fit our timeline. These observations demand explanation. They might be explained within conventional physics, through better understanding of galaxy formation, through adjustment of cosmological parameters, through recognition of observational uncertainties. Or they might require something deeper. They might require us to revise our understanding of time itself, to recognize that time is not the fixed background we assumed, but a dynamic, emergent, variable feature of reality. If time is variable, the impossible early galaxies become possible. They are not anomalies, but evidence that the temporal structure of the early universe differed from our own. This interpretation is not proven. It may never be proven in the sense that a mathematical theorem is proven, but it may become increasingly compelling as observations accumulate and conventional explanations fail. And if it is correct, everything changes. If time can vary, causation is not universal. The relationship between past and future, between cause and effect, is local rather than fundamental. Different regions of space-time might have different causal structures, different arrows of time, different temporal dimensions. If time is emergent, existence is atemporal. The fundamental reality is a timeless structure from which temporal experience arises. Our sense of flow, our memory of the past, our anticipation of the future, these are features of our perspective, not of reality itself. If the early universe had different time, the Big Bang was not the beginning. Time extends beyond the conventional beginning, perhaps infinitely, perhaps cyclically, perhaps in ways we cannot conceive. The question, what came before, has an answer, even if we cannot yet specify it. These are profound implications. They challenge our deepest intuitions about reality. They suggest that the universe is stranger than we imagined, and that our imagination, shaped by our temporal experience, may be inadequate to grasp its full strangeness. The clock is reversing. Or, more precisely, the clock was differently built, differently calibrated, differently running in the early universe. What we see in JWST images are the hands of that different clock frozen in positions that our clocks cannot replicate. We are only beginning to understand what this means. The observations are new, the theory is developing, the implications are still being worked out, but the direction is clear. Time, the most fundamental feature of our experience, may not be as fundamental as we thought. And if time can vary, what else might vary? Space, causation, logic, the laws of physics themselves? The JWST observations are a crack in our assumptions, and through that crack we glimpse a reality far stranger and far more wonderful than our limited perspectives can encompass. We will keep observing, we will keep theorizing, we will keep pushing against the boundaries of our understanding, and perhaps someday we will understand time not as we experience it, but as it truly is. Or perhaps time, like existence itself, will remain forever mysterious, forever beyond the reach of creatures embedded in its flow, unable to step outside and see the whole. The clock is reversing. The universe is teaching us humility. And in that humility lies the beginning of wisdom.